The title of this presentation is Error Correction, Authentication, and False Acceptance Probabilities over Noisy Quantum Channels. To begin with the presentation overview, I'll be discussing some work that I'm going to be submitting to the archive soon. It's pretty much finished at this point, in which I'm going to be talking about and discussing and introducing encoding, decoding, transmission, and authentication protocols that are resilient to the presence of noise. These types of protocols and these types of encoding and decoding schemes often emerge when Alice and Bob are trying to transmit some classical bit code words that are transmitted over a quantum channel. And then, but on the other hand, in addition to their activities and the encoding and decoding schemes that they choose and make use of, there's another nefarious actor, Eve, which is attempting to eavesdrop on their communication and to actually introduce some type of tampering or corruption of their messages which can be placed into their authenticated, which she hopes she can place into their authenticated set of messages. And the overall reason that I'm going to describe and further get into the game theoretic aspects of this type of communication protocol and this type of scenario in which we're making use of classical communication of bit code words over a quantum channel, is so that we can resolve one open question of interest in the literature with regards to converse results on the bit transmission rate. The bit transmission rate is just the rate at which Alice or Bob choose to transmit some fixed number of bits when they're actually performing some encoding and decoding protocol for communicating over the quantum channel. And such rates are important for determining whether there are any physical fundamental limits for error correction and authentication, because actually, even though there was some lower bound provided for the bit transmission rate in a previous work, the author that whose work I'm going to describe and further mention and allude to at several points at this presentation in the series and other presentations and other upcoming parts of the series is that this limitation is actually not really physical. It's actually more dependent upon the mathematical argument rather than actually reflecting some type of physical aspect or physical limitation of the quantum information and classical information that's being transmitted. And in doing so, we'll want to determine how previous works of quantum information theory can be of use, and this altogether will allow us to elaborate further upon the paradoxical nature of quantum physics I'm even going to begin describing in the next slide. And so, to begin our discussion of this group of topics, we introduce noisy communication over quantum channels, and as I alluded to in the previous bullet point, the action of the eavesdropper Eve on classical bit code words that can be transmitted to Alice or Bob and how this in fact has connections with optimization through primal feasible solutions of semi-definite programs, abbreviated SDPs. And on another series on my channel from a previous work that I'll even get to and describe further, I really delved into and described in a lot more detail semi-definite programs and the types of assumptions and the types of game theoretic circumstances and scenarios that these types of constraint optimization procedures arise in. So pretty much if the viewer actually wants to get more of an idea about where these semi-definite programs and primal feasible solutions arise from, the presentations in that series actually provide a bit more of a description than what I'm going to be providing in this presentation. And as I mentioned in the previous slide, the assumption that we need to incorporate is that the noise level over the quantum channel shared between Alice and Bob is larger than that over the channel that's shared between Bob and Eve. And this is just, again, relating to the fundamental setup of this type of quantum communication protocol and quantum information processing task that we're going to be describing, because Alice and Bob can actually achieve this proposed source of quantum advantage in spite of the fact that the noise over their channel is significantly greater or can even exceed or stochastically dominate the noise over Bob and Eve's channel. And the whole reason that Bob and Eve have their own channel is because Eve is attempting to map with high probability messages or bit code words that she receives that Bob has or that Alice sends into the channel between Alice and Bob into the authenticated set of messages, which I'm going to describe further in later on in the presentation and also throughout other parts of the series. And the authenticated set of messages is important because it's reflecting the information processing steps and tasks that Alice or Bob alike have to take in order to determine whether the message that they're, or the bit code word or the classical message, which is consisting of bits and classical information, is actually belonging to or actually is actually sent from another type of player that they can be confident about when pursuing this information processing task. And in a previous work, due to Ostrev, which is what I've been describing, he's talking about ways to have composable security without a secret key. Quantum key distribution is something that's really of interest for a lot of researchers in the field because it's pretty much a counterpart to a key distribution in the classical sense. And there are so many types of applications in terms of classical or quantum key distributions, in terms of encryption, cryptography, which also has some connection to some of the focuses and efforts in this work that I'm describing for the viewer right now, in the sense that he provides an inequality that was satisfied in terms of the bit transmission rate, with the lower bound being dependent upon the mutual information and conditional Shannon entropies. This is the specific form of the bit transmission rate R, which is given by the fact that it's upper bounded or it's upper bounded by the supremum over P of X. And I'll define a lot of these quantities more formally later in this presentation, but now I'm just providing a more general expression of the bit transmission rate and how that will actually relate to the converse result that I'm going to be providing also. But the bit transmission rate is, or the expression, or the range of possible bit transmission rates is actually given by multiple problems that are taken together simultaneously, in the sense that we're taking a supremum over P of boldface X, which is a supremum over probability measures over the alphabet that Alice uses. And then what we're actually doing within this supremum of a probability measure with respect to Alice's alphabet, we're taking a minimum of the mutual information entropy between Alice's alphabet, boldface X, and Bob's alphabet, boldface Y, in addition to the minimum over Z, where boldface Z is denoting Eve's alphabet. So pretty much Eve is fixing some instantiation of her alphabet to a single letter and is looking at the minimum of the conditional Shannon entropy minus of the conditional Shannon entropy taken with respect to Q, where Q denotes the probability measure that Eve uses for introducing noise into for that Eve uses for introducing a generalized noise model over a quantum channel that's actually being leveraged to as in terms of the conditioning from boldface Y, which is Bob's alphabet. And when we're also subtracting off I'm sorry, excuse me. And we're actually subtracting off the conditional Shannon entropy with respect to a different probability measure, P, which is one of the probability measures that Alice and Bob can use of boldface Y condition on X. So this is pretty much providing some type of expression for the the constraint optimization procedure that we're using for defining the bit transmission rate and how that actually relates to the converse result. And in fact, this is important because it's demonstrating, as I'll try to emphasize for the viewer throughout different parts of the presentation in the series, the competition between the mutual information entropy given by I and the conditional Shannon entropy given by H, and how these actually these various forms of entropies come into play for the bit transmission rate. And on top of the expression that we can give for R, the bit transmission rate, and different types of physical limitations or inequalities that were provided by Ostrev in his previous work in being able to provide composable security without a secret key, it's also of fundamental importance to characterize the probability of Alice and Bob being able to perform error correction, in addition to Bob being able to perform error correction over the channel that he shares with Eve. And pretty much error correction, generally speaking, it's a very important aspect of quantum information because it's pretty much determining what is the probability of Alice or Bob, or even more complicated, or even players, or even multiple players in more complicated communication protocols, to be able to detect phase errors in bit flips, which can result in errors to quantum information that's being processed over some type of quantum circuit or quantum or more complicated quantum architecture through time evolution. And just to formally define these quantities for error correction, we define the probability of error correction, little p, of error correction between A and B as just probability of big EC, namely the set of all instances of error correcting codes over Alice's and Bob's quantum channel, as well as similarly the probability of error correction over Bob and Eve's quantum channel, just replacing A between A and B instead with B and E to represent the quantum channel shared by Bob and Eve, in addition to also the probability of authentication, namely the probability that Alice and Bob, or even Eve, can authenticate some type of classical bit code word that they're receiving so that they know with high probability and with certainty that it can actually that bit code word and that classical information and that classical message was in fact transmitted from another party with confidence so that they can actually perform further pre-processing or post-processing steps on that classical information. But to generalize a counterexample, which was originally provided by Ostreb, which demonstrates that proposed sources of quantum advantage can be achieved over the quantum channel shared by Alice and Bob, despite Alice and Bob's channel having greater noise in comparison to the channel shared by Bob and Eve, we quantify the overlap of letters used by Alice and Bob in their responses. And this is pretty much given by the fact that actually, um, paradoxically, or counterintuitively, quantum advantage can be realized by just determining which letters of the alphabet each player uses and determining whether that overlaps with the letters that the adversary Eve uses. Because if we think about it, if we actually just have Alice, Bob, and Eve being, participating in some type of information processing task, or they're playing some game together to maximize their utility or some functional, which is representative of their utility, then pretty much it amounts to determining whether they can anticipate with high probability or with high certainty whether Eve is going to be sending any types of letters from her conditional probability distribution that I introduced in a previous slide from Ostreb's expression on the bit transmission rate that was given by Q, and whether that actually overlaps with probability 0 or 1 from any of the letters that Alice or Bob use when receiving a message from the other player. And this is given by the fact that this is a novelty of the work that I'm describing for the viewer because I really further delved into mathematically explaining and formulating sets of conditions with, as I mentioned in the previous slide, the error correction, the authentication, and the false acceptance probabilities for communication over a noisy quantum channel, and how that relates to this function, script O of boldface X, Y, and Z, namely script O of which is being a function of the alphabets of Alice, Bob, and Eve, which is identically equivalent to the union over little x in boldface X, little y in boldface Y, and little z in boldface Z of script O of X, Y, Z. And the overlap function, which I'm describing as being, a function which can allow us to determine whether there is any overlap between the letters that Alice, Bob, and Eve together use for providing their responses, or providing or constructing classical bit code words that are transmitted over the quantum channel, is given by the fact that the overlap function is identically equal to the empty set if and only if we're taking an intersection over all z, little z, and boldface Z, namely all of the possible letters that Eve can use, which is intersected with, in turn, the intersection over little y, namely little y and boldface Y, which is intersected with all of Alice's alphabet, is identically the empty set, in addition to the fact that this itself can also be framed in terms of an equivalent condition through an if and only if correspondence from the fact that we can also take the intersection over little x and big X, namely all of the all of the letters little x, which are belonging to Alice's alphabet, which are intersected with Bob's alphabet, boldface Y, while still maintaining an intersection over all of the possible letters of the adversary, the eavesdropper, Eve's alphabet, boldface Z with the little Z letters. In a previous relevant work in quantum information theory, some of my own work that I just wanted to briefly introduce from previous efforts that I participated in. And yeah, this work has been under review for like 4 or 5 months at this point, and is pretty much describing how to further generalize and further look at an application of another argument due to Ostreb, which was pretty much reflecting upon the fact that there can be many ways to formulate sets of relations, whether exact or approximate, which are characterizing optimality in quantum game theory. And he had originally discussed these types of sets of relations in terms of XOR games and CHSH games, and also CHSH of N games. But I basically was thinking about in the shorter preprint that, it's like 20 or 25 pages, how to further leverage some of his arguments for XOR star and FFL games. So basically, passing to duality for the XOR game and also looking at FFL games, which is interesting because an FFL game is related to the XOR and the XOR star games because they share in the commonality from the fact that they're both two-player games, but the FFL game differs from the XOR and the XOR star games because it differs in that there's a different probability in the assignment of one response from a player in comparison to these two games, which I've also discussed more in the previous presentation that I gave on my YouTube channel, in which I was pretty much discussing how, surprisingly, this difference in one probability of a response from a player, it really can have very significant ramifications and a very significant effect in terms of what the player or what notions of exact and approximate optimality we could actually argue and be able to derive with several computations involving the Frobenius norm and related types of objects. And now I'm just going to introduce some of the objects from this work briefly and actually to establish continuity with the multiplayer setting, which can then help us characterize from a more broad in a more full perspective, I guess we could say, about these communication protocols over noisy quantum channels that I've been trying to motivate for the viewer. And this is just basically given by the fact that when we're talking about game theory and quantum game theory in particular, we're looking at taking, taking a supremum over all admissible strategies to formulate the bias of a game. And the bias of a game is just pretty much determined by the following object. It's being formulated in terms of a supremum over all possible strategy script S in taking the bias beta of the game G, which is dependent upon script S. And when we take the supremum over the script S, this dependency of the bias just falls out in terms of the set of all possible strategies that we're taking the supremum over to just depend upon the game itself. And the 2 XOR game can be formulated in terms of its bias from a couple of outer products. An outer product is just given by similar to what is an inner product in linear algebra because Brockett states in quantum mechanics and quantum physics and quantum information theory, after all, they're just inner products of vectors in a Hilbert space. And this is given by the fact that when we're looking at the 2 XOR game, we're taking an outer product of two terms because it's demonstrating that the first term, which is appearing in the left-hand side of all these outer products, is given by ket I, ket j, ket I, or ket j, or minus ket j, which is given by the fact that these are the possible list of responses that one player can provide when he or she is participating in the game. Whereas the other term, which is appearing in the outer product, is reflecting upon the fact that these are the other terms or the other possible set of responses within the Hilbert space that the second remaining player in the game can provide. And each one of these outer products, given by the fact that the last outer product has an anti-commuting term, which is reflecting the fact that this term is actually constituting a losing strategy that's pejorative for maximizing the winning probability of these players in the 2 XOR game is given by the fact that they're respectively established, or they're respectively in correspondence with a sub I, b sub ij, a sub j, b sub ij, a sub I, b sub ji, and minus a sub j, b sub ji. And again, like I had been describing in the previous slide, the optimal value of the game, or the maximum winning probability of the 2 XOR game, satisfies this expression. Namely, we're forming a bracket state in terms of these four outer products that I provided in the previous slide on the presentation, and we're taking a summation over them over all possible questions I and j, taking into account the fact that there are little n possible questions that can be distributed to the two players from the referee's probability distribution. And then what we're also doing is that we're taking a supremum over the wave function psi, namely the optimal state for Alice and Bob so that they can win the game. In addition to the fact that we're also taking the supremum over these tensors A sub I and B sub j, namely the tensors of observables for Alice and Bob. But also, it's important to note that we're taking a normalization in terms of 1 divided by 4 and choose 2, namely taking into the fact that if the referee's probability distribution has little n questions in total, we're dividing and we're normalizing the summation of for which is corresponding to the maximum probability that Alice and Bob can win the 2 XOR game by the total number of ways times 4 of distributing little n questions to each one of the two players. And to study anti-commutation relations and quantum information theory, what was really central to Ostrev's framework that I've been describing and alluding for the viewer that I analyzed in that previous framework, in that previous paper that's been under review for the XOR star and FFL games, is given by the fact that we have to formulate a set of suitable linear operators. And for the 2 XOR game, these operators are pretty simple because they're just pretty much relying upon the fact that we're mapping from a tensor product of two Hilbert spaces, which are corresponding to, in some rough sense, the set of possible responses that Alice and Bob can have for each other. But as I mentioned to the viewer in another previous paper, which was given by the previous presentations and series that I posted on my YouTube channel, I significantly generalized Ostrev's framework and discussed several types of more complicated game theoretic situations in which this framework could arise in terms of multiplayer games in strong parallel repetition and ordinary parallel repetition of games. And looking at these types of games beyond the two-player case, it's very important and very interesting and enlightening because it's pretty much determining what are the fundamental limits or barriers or difficulties for having prospective quantum advantage for various information processing tasks. And this is given by the fact that, as I just described for the viewer, for the 2 XOR game, the suitable linear operator T is given by just mapping from a tensor product of two Hilbert spaces into basically the set of all possible responses for Alice and Bob. Whereas for the 3 XOR game, we're just adding another Hilbert space to the tensor product in the preimage and in the image, or in the codomain in the image of the mapping that we're looking at. And there are several variants of these types of suitable linear operators that we can look at, namely given by the fact that, again, like I mentioned, the TXOR game, or the TXOR suitable linear operator T of XOR, which is given in the second line on the transparency, is given by the fact that its preimage is given by a tensor product of two Hilbert spaces, which is mapping into the tensor product of C of D of A and C of D of B, namely the complex valued space, or the Hilbert space, corresponding to the set of all possible responses from Alice, tensor product with the set of all possible responses for Bob. And then pretty much we can look at other types of ways to formulate these suitable linear operators, namely if we're taking tensor products, we're looking at a tensor product of suitable linear operators for the XOR game. We're taking a tensor product over n copies of this Hilbert space, and we're mapping into a tensor product of however many Hilbert spaces corresponding to the set of all possible responses for however many participants there are in the XOR game. And then, but the suitable linear operator takes a little bit of a different form of an expression when we're looking at the fourth operator that's provided in the line on this slide, because we're looking at performing the strong parallel or ordinary parallel repetition operator, which is given by this wedge symbol. And the wedge of T of XOR is just given by the wedge of each one of these Hilbert spaces, which is mapping into the wedge of each one of the Hilbert spaces or complex valued spaces boldface C, which is given by each one of the possible expressions or each one of the possible Hilbert spaces in taking the parallel repetition operation of these spaces all together simultaneously. And then we can also look at an equivalent way to express the parallel repetition operator of the XOR game, namely T of XOR wedge XOR itself, an arbitrary number of times, which is related to the expression for the parallel repetition operation of the suitable linear operator in the previous slide, except that we're distributing the parallel repetition operation to the actual exponent and how many elements are in each one of the Hilbert spaces corresponding to the responses from each one of the players in the pre-image and in the image of this mapping. And then finally, we can also kind of look at more of a narrow and restrictive setting for performing parallel repetition for the FFL game, because for the FFL game, pretty much what we end up doing is that we're just taking parallel repetition twice. And this is actually exhibiting a pretty significant difference already from performing some arbitrary number of parallel repetitions for the XOR game in comparison to the FFL game, because as I discussed in the previous presentation in a previous presentation for some other work that I'll describe and allude to later in this presentation of this series, there's a fundamental difference in terms of the optimal value of the FFL game being equal to itself, or what I described in terms of as being invariant, namely the fact that the maximum winning probability for the FFL game before and after one performs parallel and ordinary and strong parallel repetition is equal to 2/3, but that this equality between the maximum probability of winning an FFL game doesn't at all hold for the XOR game, which is already demonstrating a fundamental difference between these two games, which, as the viewer can recall, as I described and alluded to, is resulting from the fact that there's a difference in only the assignment of one probability in these games, which is something that's very striking and very interesting to theoretically explore. And the referee's scoring predicate, namely the function that the referee uses for determining whether Alice and Bob win the game, is given by the following expression. Namely, if we have the questions little s and t, which are distributed from the referee's probability distribution to Alice and Bob respectively, he or she can form a predicate which is dependent upon the answers little a and little b, which are received from Alice and Bob, which is identically 1 if 1 minus the Kronecker delta of the questions little s and little t is equal to the direct or the XOR sum or the direct sum of a and b, and 0 otherwise, where the Kronecker delta is given by being identically 1 if s is equal to t and 0 otherwise. And we can denote, as I said earlier, but now I would like to formalize a bit more, we can denote the set of all admissible error correcting codes with the following, namely big EC being identically equal to a union over a little EC, where each one of these little EC terms within the broader class of error correcting codes denotes the error correcting codes EC over a quantum channel. Whether the quantum channel obviously has noise or not can be something that the error code can accommodate in terms of trying to detect, as I mentioned for the viewer earlier, bit flips and phase errors. And also, to formalize a bit more, we can denote the probability of false acceptance with the following. The false acceptance probability, generally speaking, is important because it's actually determining the situation or the unfortunate scenario in which Alice or Bob can accept a message that they think came from their other player or their counterpart, but actually wasn't tampered with by Eve. But actually, it was. And in this case, we have to actually account for the effect that a probability of false acceptance can have in terms of mapping bit code words like I described for the viewer into some authenticated set of all messages over their channel, even in the presence of noise. And unfortunately, generally speaking, this can introduce complications because if Alice and Bob then have some types of spurious messages, so to speak, or messages that they really shouldn't have accepted that were really tampered with by Eve, but actually that from their perspective, from making use of their authentication protocol, they thought were actually messages that were transmitted from their counterpart or the other player in the game, Alice or Bob, who's not the eavesdropper Eve, then this can basically introduce a lot of types of ways in which we have to reflect upon how we have to ensure or guarantee that error correcting codes can be used to mitigate or pretty much decrease as much as possible the probability of false acceptance. And specifically, explicitly, this probability of false acceptance is given by the fact that its probability P of FA, of capital FA, being a minimum, namely the minimum or the infimum over all instances of false acceptance little a over big F of A of this probability of little f of A, namely being the infimum of the failure probability of a player accepting a message that should have not been accepted, namely a message that was tampered with that they didn't know or that they weren't aware of was tampered with by Eve. And the set of all instances of false acceptance for Alice and Bob is denoted with the following set, namely big F of A being identically equal to a union over little f of A, namely the instances of all false acceptance little f of A over a quantum channel. And furthermore, as I described for the viewer and introduced previously, when we were talking about the bit transmission rate that Ostrov had introduced in his previous work, as well as trying to draw the attention of the viewer to the counterexample that he provided, in which he pretty much said that there were pretty much alphabets which were like 2 or 3 letters long for Alice, Bob, and Eve, so that Alice and Bob did not have to satisfy error correction and authentication protocols that could still be achieved in the presence of greater noise over their channel. This is pretty much related to these following types of objects that I want to describe and further delve into now with the viewer, so we can formalize things a bit more. And this is given by the fact that we have little x and y, not boldface x and boldface y, but just little x, or x and y without the boldface, which is given by two realizations of the random variables from Alice and Bob's alphabet. So pretty much it's going to reflect upon the fact that we need to introduce probability measures for Alice's and Bob's alphabet, which are then going into the fact that these are entering as constraints into the constraint optimization procedure that we're using for being able to quantify properties of the bit transmission rate. And then also right below these two realizations of random variables from Alice's and Bob's alphabet, we have boldface X and boldface Y, which are respectively given by the collection of random variables or the collection of letters which are being used from Alice's and Bob's alphabets. And then we can define P of X, not P of boldface X, just P of X, namely as a probability measure on a realization of whatever letter or whatever random variable Alice and Bob are using for their quantum channel. In addition to the fact that we're looking at a probability of P of boldface X, which is entering in terms of the supremum for the expression for the bit transmission rate, which is given by a probability measure on boldface X, which is identically equal to a union of probabilities P of X, where X is belonging to boldface X, as well as P of Y, just P of regular Y, which is a probability measure on Y, namely some random variables that Alice and Bob are using as letters from their alphabet, in addition to P of boldface Y, which is identically equal to the union over little y, or over y and boldface Y of P of Y, which is collectively together the set of probability measures on boldface Y. So this is just formalizing a bit a lot of the probability measures and expressions which we're giving, which are coming into play in terms of either, quantifying the limitations of, pronounced quantum advantage for communicating classical bit information over quantum channels, in addition to the fact that these probability measures that I've provided and I've drawn out and spelled out further for the viewer on the slide, they're really coming into play exactly in terms of the constraints from the optimization which we're using to quantify the bit transmission rate. And then, this is pretty much also relating to the converse result that I'm going to be eventually introducing in the next presentation and further along in this series for the bit transmission rate. And so recall the lower bound on the bit transmission rate provided in Ostrov's previous work. So just basically that we were talking about the bit transmission rate R, and we were drawing the attention of the viewer to the fact that it can be expressed in terms of a constrained optimization procedure from like with multiple layers, because we're taking a supremum over P of boldface X, and then we're taking a minimum between the mutual information entropy and the conditional Shannon entropy. And then we're also taking a minimum over the letters that Alice can, or that Eve can choose from her alphabet for trying to corrupt a message that's being transmitted from Alice to Bob, or from Bob to Alice. And as we had been mentioning, that we want to introduce is that the converse result on the bit transmission rate is given by the following inequality, just switching the direction of the inequality for the bit transmission rate while maintaining the supremum over P of X and the minimum of the mutual information and Shannon entropies, as well as the minimum over Z of the conditional Shannon entropy identical. And this is identified as something that would be interested to be explored, like I mentioned from Ostrov's previous works, because he pretty much is looking at the fact as to whether there could be any converse result, namely some type of result that you would like to have, that one would like to have for the bit transmission rate, in which you reflect, or which you, sorry, not reflect, but you reverse, you flip the direction of the inequality, and how that's pretty much reflecting upon paradoxical aspects of quantum information, because this bit transmission rate could be used to construct error correction and authentication protocols, which could be resilient in the presence of noise that Alice and Bob can execute. And now I'm going to actually provide an explicit form of the upper bound of the bit transmission rate that's obtained in the converse result from my new work that has been coming up, and to actually discuss how this relates to different aspects of what we've been talking about and motivating throughout this first presentation of the series. So basically, what we want to do is that we want to see if there's some type of way to upper bound this supremum over the probability measures P of boldface X in terms of the minimum of the mutual information entropy with the conditional Shannon entropy, and as well as also taking into account in terms of minimizing the conditional Shannon entropy from letters that Eve can pick from her alphabet for eavesdropping purposes. And this is just basically given by the fact that, like I had mentioned, I define some extra or additional auxiliary alphabets which are introduced, because basically it's given by the fact that if we want to generalize Ostrov's counterexample that I described and motivated for the viewer, in which there's some way basically for Alice and Bob to determine with high probability that if there's a message that comes with some letters that are exclusively used by Eve's alphabet, that they can basically be able to minimize the probability of false acceptance, and to be able to reject these messages immediately like that, or immediately without actually having to further perform any types of decoding protocols, or actually any other types of authentication protocols which are associated with Eve's transmission when she's trying to map her corrupted message into their noisy quantum channel. And this is basically given by the fact that, as I'll describe in future presentations in this series, you can look to basically upper bound this supremum term in terms of logarithms, natural logarithms. In fact, with the fact that it's being dependent upon this logarithm of y of the cardinality of y star, where boldface of y star is some pruned alphabet that's used by Bob. And by a pruned alphabet, I mean an alphabet which is strictly smaller in cardinality to the original alphabet that Alice or Bob originally started playing the game with, but it has some letters removed so that they can maintain their prospective quantum advantage and just basically obfuscate the total number of letters that they're going to be using so that Eve from her attempts to eavesdrop on their communication and from also from her attempts to try to introduce some type of corrupted message into their noisy quantum channel and hence into the authenticated space of all bit code words can actually maintain and preserve the prospective quantum advantage that Alice and Bob can hope to have in terms of being able to simultaneously execute error correction and authentication protocols with high probability, despite the fact that there's more noise over their channel in comparison to the noise over the channel between Bob and Eve. And pretty much it's depending on a case by case scenario because obviously there are many possibilities in terms of the total size of the alphabets that Alice and Bob can use, as well as maybe the letters or the spurious letters, which I'm calling them, that they could remove from their alphabets, which could actually help them maintain prospective quantum advantage and could actually serve as an obstacle for Eve, who's trying to basically use as many letters as possible so that she can try to confuse Alice or Bob on the receiving end over their noisy quantum channel in terms of trying to basically trick them to accept a message from her that they think was actually used or transmitted or constructed or decoded or encoded from the other counterpart player. And basically, in this upper bound to the bit transmission rate that's given in this converse result, there are several other types of terms in which we can have, in terms of this first log term, we can have a log of the cardinality of boldface x, which is normalized by the cardinality of y star, or we can have the natural logarithm of the cardinality of y star normalized by the cardinality of x star, or we can even still have this same contribution, which is appearing in the first log term. And there's also another contribution which appears in the upper bound in terms of just a log term, and the difference of a log and a log term in terms of these two contributions to the upper bound from the converse result on the bit transmission rate. It's emerging from some aspects of the upper bound and computation of the upper bound from the second main result of this upcoming new work that I've been describing and motivating for the viewer that I'll describe more in other presentations of the series. But it's just pretty much coming into play that we can look to upper bound different types of contributions by taking natural logarithms, because if we even imagine as an initial step to compute some type of upper bound for the bit transmission rate or for the converse result on the bit transmission rate, we're pretty much taking a natural logarithm of this constraint optimization procedure, which is strictly upper bounding the original constrained optimization problem, which we're phrasing in terms of the supremum over P of X, and then the minimum of the conditional Shannon entropy or the mutual information entropy with the conditional Shannon entropy, and then taking the minimum over the conditional Shannon entropies. So this is just pretty much some type of broad overview of the upper bound on the bit transmission rate that I wanted to provide for the viewer, that I'm going to revisit at several parts throughout the presentation of this series, but that I thought would be informative just to first provide some type of salient features of this strict upper bound for the bit transmission rate and the converse result, namely given by the fact that we're looking to generalize the counterexample for maintaining prospective quantum advantage for error correction and authentication protocols, namely that these protocols can be enacted by Alice and Bob with high probability, in addition to the fact that sometimes, unfortunately, if we're taking alphabets for Alice, Bob, and Eve to be of an arbitrary size, there may be some instances in which maybe they could maintain some prospective quantum advantage by being able to remove letters or throw out letters from their respective alphabets of Alice and Bob, which would then actually really help them in terms of maintaining the prospective quantum advantage of being able to perform error correction and authentication with high probability, because then Eve would pretty much have a smaller, more narrow, restricted range or set or collection of letters from her alphabet that she would have to use when for her responses in mapping into the noisy quantum channel over Alice and Bob, which probabilistically speaking, it makes it much more difficult for her to succeed in the task of being able to introduce some type of corrupted classical bit code word that can be mapped by Alice and Bob mistakenly, unfortunately, into the authenticated space of bit code words. And the second stochastic domination result from theorem 2, which I'm going to be describing in the next presentation in terms of the three main results and how this actually relates to the first main result, which was given on the previous slide for the upper bound for the bit for the converse result and the strict upper bound for the bit transmission rate, is given by the fact that we're looking to form some type of stochastic domination between the error correction and the false acceptance probabilities over the quantum channel that's shared between Alice and Bob, namely given by this ratio. The probability of error correction of Alice and Bob normalized by the probability of false acceptance. In the computation of the second stochastic domination result provided in the previous slide relies upon the computation of the following probabilistic object. So pretty much we're fixing some constant, some strictly positive constant CC to be greater than 0. And we're taking a supremum over all error correcting codes between Bob and Eve's quantum channel. And this is pretty much expressed in terms of a condition on the overlap function. So basically, we're taking a supremum over all instances of error correction, little e sub b, little e sub c, which belong to big E sub c. And we're pretty much determining as a union over all the letters, little y in big Y and little z in big Z, namely all the letters that Bob and Eve can use, what's basically the dependence of this numerator term in terms of the probability of false acceptance between Alice and Bob's channel, conditionally upon the fact that Bob and Eve make use of the alphabets Y and Z, namely the alphabets for crafting or for making or for encoding their responses, which are dependent upon just the letters Y and Z. And to analyze the conditional probability provided on the previous slide, we make use of Bayes' rules at several points of the computation at like 3 or 4 times to be specific, which is allowing us to update the prior in this particular manner. Namely, when we apply Bayes' rule, we can switch the conditioning with the event itself and be able to basically multiply by the first event that we had in the original probability and divide by the conditioning. And this is just given by the fact that if we're looking at the probability that for all C star being a real constant, there exists some error correcting codes such that the overlap between the letters that, the alphabets that Bob and Eve use being greater than C star, while the players being able to simultaneously perform error correction conditionally upon the fact that these are the letters that they use in for generating their alphabets. This is given by just the probability that they use these alphabets conditionally upon the fact that they can perform error correction and that there exists some suitable threshold for the overlap function, which is given by C star. And then pretty much the two remaining terms that we have in these probabilities are given by dividing by the probability of the conditioning, namely the probability that Bob and Eve use alphabets Y and Z, in addition to the probability that there exists some suitable threshold for the overlap function. And again, like we mentioned, the overlap function is just a very helpful generalization of the counterexample which Ostrep had given, in which he pretty much describes how Alice and Bob can maintain their prospective quantum advantage even in the presence of alphabets with a few letters, despite the fact that there's more noise over their channel. And the probability of Alice and Bob generating an alphabet for formulating the bit code words that they transmit over their shared quantum channel is given by this expression that we had introduced in the conditioning from the previous slides in the probability for the probability of having some suitable threshold for the overlap function. And also, relatedly, the probability of players using letters from their respective alphabets simultaneously is given by the following expression, namely the probability that alphabets X star Y Z or alphabets X Y star Z are used is just identically equal to the probability that Alice, Bob, and Eve respectively use alphabets X star Y and Z, or the probability that Alice, Bob, and Eve respectively use alphabets X, Y star, and Z. And one assumption that we make use of quite a bit in terms of lower bounding the product of probabilities is given by the following, which roughly states that the conditional probability of the overlap function being a non-empty for infinitely large alphabets of Alice and Bob, or for Bob and Eve, asymptotically approaches zero. And this is pretty much really helpful because one can recall that I defined the overlap function in terms of three alphabets, boldface X, boldface Y, and boldface Z. But really, this is actually helpful because we can basically restrict the overlap function just to Bob and Eve's alphabet from the overlap function, which is given by the alphabets from Alice, Bob, and Eve, so that we can obtain some type of desired lower bound or some desired stochastic domination result that I'll describe further in the next presentation of this series, which is pretty much relating to the fact that the probability of performing error correction, despite the fact that there's more noise over Alice and Bob's channel, is strictly larger than the probability of being able to perform error correction, and hence also relatedly of authentication over Bob and Eve's channel. And this is given by the fact that when we're taking these two limits, which are given in the front of these supremum of the supremum over all error correcting codes of these conditional probabilities, we're pretty much looking at taking the cardinality of Bob's alphabet and of Eve's alphabet to infinity, while we're simultaneously taking some other threshold parameter for the overlap function C star star to approach zero from the positive side. And as is demonstrated from this probability, this conditional probability upon the fact that Bob and Eve use alphabets Y and Z for encoding the responses of classical bit code words that are transmitted over a quantum channel, the probability that there exists some suitable sequence of strictly positive constants, namely C star star, C star, and C, which are real, for which there exists an error correcting code for which they can perform error correction with positive probability, is given by the fact that this is stochastically dominating the probability that there exists another threshold for the overlap function, which is given by C star star, which is different from C star star, in which, but it's still approaching zero from above, namely C star star is going to zero from above, which is given by the fact that it's a very similar probability, except that the threshold for the overlap function between Bob and Eve's alphabet is exceeding C star star instead of C star star star. So basically, this probability from the C star star threshold is strictly dominating the probability of the overlap function exceeding some threshold C star star, which is helpful at various points when we're performing computations for the main result for theorem 2 for demonstrating that a desired stochastic domination holds. And we make use of the following approximate expression for the error correction probability over the quantum channel shared by Alice and Bob, namely given by the fact that we're incorporating a similar type of condition, namely we're taking a supremum over all error correcting codes from between Alice and Bob's channel, and we're looking at the probability that there exists some C star constant, which is real, for which there's also some error correcting code or some suitable class of error correcting codes for which the supremum of the overlap function between X star, Y, and Z, or of X, Y star, and Z is greater than C star, while allowing the players to simultaneously achieve error correction conditionally upon the fact that they either make use of the alphabets X star, Y, Z, or alphabets X, Y star, Z for their encoding of classical bit code words that are transmitted over the quantum channel. In the previous relevant work that I've been describing from myself on quantum information theory earlier in this year, the first version of which was in May, in which I updated, some minor updates around like a month and a half later, is given by the fact that we're generalizing various multiplayer settings, like I mentioned for the player or for the viewer earlier in the presentation, which is relating to quantum strategies, error bounds, optimality, and duality gaps for a wide variety of multiplayer settings. And this is pretty much relating to the fact for this information processing task that I've been giving in terms of introducing classical bit codewords over quantum channels, because it's pretty much allowing us to determine what are the limitations and actually prospects for quantum advantage, which are dependent upon noise. And as I mentioned for the viewer, but now very briefly to formalize, the parallel repetition of the optimal value for the XOR game stipulates that the maximum probability of winning an arbitrary number of parallel repetition rounds for the XOR game is given by the product of each one of these maximum winning probabilities, which is significantly different already from the parallel repetition, whether strong or ordinary parallel repetition for the FFL game, because the FFL game maximum winning probability is the same before and after performing parallel repetition. And the semi-definite program, like we mentioned, has a lot of connections with the type of constraint optimization procedure which we're using to try to analyze the bit transmission rate, which is given by a completely kind of different communication protocol which is involving encoding, decoding, authentication, and transmission. Because in this case, the semi-definite program with a primal feasible solution Z prime is given with respect to a partial ordering of the positive semi-definite cone, where we're looking at some types of constraints for the 3 XOR game, namely three constraints, and then we're basically stipulating as a constraint to this optimization procedure that there exists a real constant for which some type of dual objective f sub I multiplied by the game matrix is identically c sub I. And how this relates to actually a duality gap formalism is that we can take the semi-definite program that was given in the previous slide, and we can subtract off these terms, this objective terms, y sub I, big sub f sub I, minus the game matrix for whatever game we want to look at, which is basically allowing us to determine what are the prospects for quantum advantage in terms of communication for Alice and Bob in this multiplayer setting, which is very much reflecting upon similar prospects for quantum advantage that Alice and Bob can hope to achieve for error correction and authentication from these quantum information processing tasks from transmitting classical bit code words that I've been motivating for the viewer from the bit transmission rate and from various conditions that one can place on the overlap function between alphabets of different players. And for bit transmissions rates that are not included in the converse result, the probability for, or pretty much the prospective quantum advantage is significantly relying upon the fact that the probability of Alice and Bob mapping code words with high probability into the authenticated set of all code words is dependent upon the following. Just basically the probability with respect to encoding and decoding and transmission and authentication over the shared quantum channel between Alice and Bob and Eve, that there exists some C sub n that which is strictly positive, such that the cardinality of the authenticated n-bit messages from Alice and Bob over their shared quantum channel compared to the cardinality of the authenticated n-bit messages by Eve over the quantum channel shared by Bob and Eve is strictly is much larger than C sub n. So basically, this is a significant observation that Ostrev makes use of in his work to basically classify or to basically provide some type of classification of prospective quantum advantage for bit transmission rates that are not included in the converse result. And we can study the same probability under the limit of infinitely many bits by just taking the limit as n goes to infinity and goes to positive infinity of this probability. And so now this is the end of the first presentation of this series. So I just wanted to finish up with a recap, and then I'm going to kind of describe to and allude to the viewer some types of additional aspects of the arguments particularly how the converse result on the bit transmission rate can be shown to hold and what types of computations go into place for obtaining that desired result and how that actually reflects upon, as I mentioned, generalizations of the counterexample that Ostrip provided for us through this type of pruning procedure or eliminating spurious letters from alphabets of different players. So, for the first presentation of the series, though, we began our discussion of quantum information theory, including discussing the limitations that noise can raise for various communication protocols. And we were drawing the attention of the viewer to the fact that there's a setup of Alice and Bob transmitting classical bit codewords to each other, which can be intercepted and tampered with by Eve. And the primary goal of Eve is that she wants to really be able to introduce messages that Alice and Bob will mistakenly accept into their authenticated space over their shared quantum channel. And we also provide the statement of the converse result on the bit transmission rate, namely given by the fact that we can flip or redirect or reverse the direction of the inequality for the bit transmission rate, and how this still is reflecting upon the supremum over a probability measure, the minimum between the mutual information entropy and the conditional Shannon entropy, as well as a minimum over the possible inputs that Eve can provide from the conditional Shannon entropy. And altogether, to further shed light upon how to explicitly upper bound for how the explicit upper bound for the bit transmission rate is obtained. In the next presentation of this series, we discuss how the contributions from the mutual information and conditional Shannon entropies alike determine how Eve can attempt to corrupt a bit codeword transmitted by Alice or by Bob. And furthermore, we will not only state the main results of the upcoming work, including the converse result, but we'll also discuss how one can relate upper bounds of the mutual information and conditional Shannon entropies to one another. And we will also further discuss how Alice and Bob can perform procedures to eliminate, like I mentioned at a couple of points in this first presentation of this series, to eliminate spurious letters of their alphabets so that they can determine with high probability whether a response came from Eve, albeit a greater presence of noise over their shared quantum channel. And thanks for watching.